Hello, this is Dr. Kirshner again. Once again, I'm the consultant to the Elem Pomo tribe on Clear Lake, California, the Sulphur Bank Mercury mine. This is a third in a series of lectures or webinars regarding Sulphur Bank Mercury mine. The first two lectures focused on pros and cons of alternatives number 8 and those alternatives proposed by the state of California. The lecture is more directed at Operable Unit 2, also known to you as the Lake or Clear Lake. Once again, we are new to the technology and prefer to interact with those out there instead of this one-way interaction, but I hope you find this useful. So here we go. We're reviewing the alternatives that are out there for Operable Unit 1 or the mine site itself. This is the state's preferred alternative. Generally, it's cap and cover the waste piles. These are the areas in green. These areas in brown will be moved relocated here to consolidate the units a little bit, and then capped the areas in green. Exposure from the 23-acre Herman impoundment still remains. Contaminated groundwater allowed to seep into the lake forever. From the Herman impoundment. It flows through all the bases of all these waste rocks units into Clear Lake, and we'll talk a little bit more about that in the future. The remedy is not protective of human health or the environment, especially not the tribes that use the resources. The remedy may comply with ARARs, which ARARs stands for Applicable, Relevant, and Appropriate Regulations. But the state ARARs are not protective of human health or the environment, and specifically not for the tribes that use the resources. And finally, it does not accommodate waste material from beaches or wetlands, and that's in Operable Unit 2, and that's what we're going to talk about today more. So these first two slides should be reviewed for you. This is the tribes alternative number 8. Essentially, we're moving all the waste material that was green in the other slides into the Herman impoundment, capping and covering it, and reducing the footprint of the site itself. So the alternative eliminates exposure from the 23-acre Herman impoundment because it's no longer present. It's a hill now. It fully breaks the groundwater flow path to the lake by perpetual pump and treat of the Herman impoundment. It greatly reduces the volume of Operable Unit 1 cover material, so we only have this small area that needs to be covered, and so it'll reduce trucking. Except for final cover material, all transportation occurs on site, greatly reducing costs and transportation hazard. And long-term Operable Unit 1 O&M costs, that's operation and maintenance costs, driven by water treatment plant options. You can either do on-site water treatment versus discharge to a publicly owned treatment works, and there's some benefits to the public by that if that were allowed, but we've since found out that that's less likely going to occur. And finally, this alternative accommodates waste material from beaches or wetlands that need to be dredged as part of the remedy for Operable Unit 2. Okay, now we're going to talk about Operable Unit 2. This is the wetlands portion of Operable Unit 2. Water entering the Herman impoundment from surface water, geothermal springs, overland flow occurs at a much more rapid rate than groundwater exiting via evapotranspiration, bedrock fractures, or the waste rock dam. Here's the waste rock dam again, and it results in mounding at the Herman impoundment. So again, the Herman impoundment is always running 10 feet in elevation higher than the lake, so you get flow out of the Herman impoundment through the waste rock material and then into the lake, where contaminants are transported through the base of these waste rocks material. Here's another shot of it. Again, this is the mine waste outlined in yellow here, and then there's hot springs feeding this area, and so flow occurs outward from the Herman impoundment to the lake through the waste rock. This is a generalized conceptual site model of Herman impoundment. Again, here's the Herman impoundment. This is a generic waste pile, and showing the water level is higher in the Herman impoundment than it is out in the lake or the wetlands, roughly that 10 feet difference I talked about. So this causes flow to occur from the Herman impoundment out into the wetlands or into the lake, depending on which direction you're looking at. And we're kind of looking at this eastward along the axis of the Herman impoundment, if you will. This is precipitation. You get rain or snow melt, and then you have evapotranspiration, which removes water. So as this occurs, you have acid rock drainage being produced in the waste piles due to oxidation of pyrite and other minerals, but that's predominantly the cause. And the water is carrying this saturated solution down towards the water table, and it deposits these salts. They're at the base of these waste rock piles, and some of this material is transported out. Some of it's deposited there in the unsaturated zone. Okay, and also there's a wind component as well, and then direct runoff into the Herman impoundment. Okay, so I'm not going to go through this too much, but the characterization goals for typical waste piles like this is to determine the amount of groundwater exiting the base of the ponds and piles. Well, EPA hasn't really done that. To get an idea what the surface water runoff, and then finally fugitive dust. None of these have really been addressed directly over the past 30 years that EPA has been working on this. Okay, so this is the conceptual site model along the same line. This would be the Herman impoundment sitting right over in this area. Here's a waste rock pile, and then here's the wetlands, the north wetland investigation area. And so it's showing transport occurring like I showed in the other conceptual model. This was a conceptual model put together by EPA, by Tetra Tech years ago, and nothing new here. And except they show, transport up the food chain to the fish and then ultimately to humans, but they really don't go into that degree of discussion. These are some sampling locations that were sampled by EPA and Tetra Tech and these guys years back. Over here is the Elem colony. This is the road between the Elem colony and the mine site. And again, water's flowing this way. It's flowing upward to the top of the screen into this area where you can see there's some little bit of ponding going on. And these are their sample locations. So they've got roughly 6 or 8 sample locations out there. This is another picture from showing previous sample locations. Same area. This is from their work plan. Based on the previous investigation, conceptual site model, and data quality objectives, the following media were sampled: sediment, detritus, surface water, and the biota. They sampled tadpoles, beetles, mosquito fish, shorebird, and waterfowl eggs. But none of this was helpful for the human health risk assessment because we don't eat many of these receptors. So more sampling had to be done with respect to the human health risk assessment, as well as they didn't really have a good idea on the sediment quality over time. Surface water samples per location. So here they propose to take 3 mercury and other metal samples per location. Well, it's really tough to understand something that's temporally variable with 2 or 3 samples. But they made an effort and took some samples here. This describes their plan, and it was not all that rigorous, but it's a typical snapshot. They're trying to get an understanding, and they really need to understand what the baseline concentration of metals are. That means a snapshot of what we have on the ground now, and they've done some sampling to try to characterize the sediments and surface water and some of the biota out there. And like I said, just recently, EPA is proposing to do more sampling to support the human health risk assessment associated with the use of resources by the Elem Pomo tribe. Okay, so now we're going to talk about Clear Lake Operable Unit 2. And this is actually looking south. It's a little bit different direction than we looked before. But this is just right from Google Earth. This is images in November 15th, 2011. And here's the wetlands area that's a subject that we were talking about. And you can see that there's the springs that I pointed out. They're observable on the photos. And then there's also these salt buildups, this white precipitate out here. These are actually evaporites. And it's from water flowing through this stuff, daylighting in these springs, and then evaporating out in this wetland, the floodplains of the wetland. Here's a photo from 2013, July, where it's a little bit drier. Again, the last one, let me go back. This was, towards the end of the year, where it's drier. You can see these salt buildups, and again, you see the same thing here in 2013, springs and the salts. In 2017, it was a little bit wetter, and this is actually in May, so it's earlier in the year after runoff, and these wetlands flooded, and so the salts were redissolved and retransported out into the lake ultimately. And again, the springs are present, but no salts. This is 2018, later in the year again, and again you see the springs and the salts are definitely present in the wetland area. Okay, so again, Operable Unit 1. Now we're looking north. And here's where we were within the wetland area, and Operable Unit 2 is the remainder of the lake. Again, we've looked at the area here. What we believe, this appears to be the wetland. We really don't know the nature and extent of contamination in here yet because there hasn't been adequate enough sampling to delineate or put this line on a map, if you will. We can't tell if we need to remove stuff here or remove stuff there. We just don't have that information yet. So the green line is a conservative estimate of the wetland that would need to be removed. It's a little bit larger. This is a potential area that look like it might need to be removed. And then ultimately the beach area, because all this stuff has been concentrating in the beach environment, and we will use the beach. And not only that, the plants and animals use the beach, and the plants and animals we use as a form of sustenance. So the bottom line is, just looking at this, is that the wetland acre, the smaller wetland acre, we've got acreage is roughly 50. The green polygon is 80 acres, and then the beach itself is 40 acres. And that's the areas that we believe need to be remediated, and we are advocating for dredging the beach areas and replacing with a clean sand, and then also raising this area and cleaning it out with earth moving equipment, where all of the sediments from both endeavors would be disposed of in the Herman impoundment in our alternative. Something has to happen with it. It needs to remain on site. Okay. So back to this photo again. This is showing the mine site, Herman impoundment, and again, Herman impoundment creates a mound, and all groundwater flows away from that mound, and it's flowing through these materials out in the waste rock dam. All these materials out into the lake, and this is just another depiction of it. This as well. Again. I promoted this definitely in a earlier webinar, but this is definite necessary reading for anybody that's living around the lake. It's a great work that the guys at Davis did. And I'm going to talk a little bit about the cores that were obtained out in the lake. And I talked about some of these earlier before. But this is a timeline showing that roughly in the 20s, we start getting the wetlands start dropping off because agriculture is increasing. This is probably the most important one. Agriculture takes off, livestock takes off, and so the farmers are trying to recover as much wetlands, turn it into arable lands or farmable land. And so this is what's happening here: is the wetlands are becoming reduced drastically, and livestock and ag is taking over, and that's predominantly because of the invention of the tractor. And you've seen these before. This is part of the Dust Bowl. That tractor was responsible for the Dust Bowl predominantly. Okay, so around the same era, this is when open pit mining began in the Sulphur Bank Mercury mine. Here's the lake out here, and the colonies like back over on the other side of this hill. And here we are mining out the Herman impoundment right now. So here's some cores that were sampled by Davis, actually Sekonic and Rikerson, I believe. And the mine site sits right in here. This is Oak's arm. This is the upper arm and lower arm. We're going to look at this transect first between Oak's arm and upper arm. Again, okay, here's core from the upper arm closest to the mine site. Farthest from the mine site, and then the Oak's arm. So what we see here is that before you see these big kicks come in 1927, and that's when the mining occurred. And this is Mercury on the lower axis here. So you see Mercury just trailing along. Let's say at the upper arm here at a half a ppm. Everything's this is natural background, and then all of a sudden, bang! It blows off scale all the way up to roughly 4 ppm, which is 8 times of what that background was. Well, it really happens over here by the mine site, as you would expect as well. So it's roughly, it's run around natural background there is roughly around 10, and then bam, up to 100 when mining occurs. So you can definitely see the impact of mining close to the mine site, but far from the mine site, which is quite incredible because just the transport mechanism. We'll talk about this a little bit more. So, based on the 2000 core at the Oak's arm, post-mining deposition rates appear similar to the upper and Oak's, but slightly lower in the lower lake. This could be interpreted as solids from the Sulphur Bank Mercury mine not influencing SEDS at the Oak's arm sample location, meaning that water column transport is already dominating. So let's look at these again. These are down on lower lake now, I believe. No, this Oak's arm, this is lower lake. And it's showing the lower lake and Oak's arm natural background is roughly about the same. I'd say around a half to 0.1 for total mercury on the cores. Okay, this is a conceptual site model of transport. This was something that I presented to the National Remedy Review Board, I believe in 2005, when this site was first up for review for a feasibility study. And essentially the way this operates, these are dispersion curves. So let's look at the blue curve right now, which is the most important. That's the pre-mining conditions. So pre-mining, and this is the distance, so this is the mine site itself at 0, and this is someplace along that transect out to the core, the further core and the upper arm. Well, if we only look at the blue line right now, pre-mining conditions. Pre-mining, there was a fingerprint on this from the site itself, pre-mining, that was observable. And it's just natural conditions. And so it runs out of distance if you could sample as you're going away from the mine site, and then it would start, the concentration of mercury would start dropping off naturally and come down through this dispersion dominated zone until you reach natural background. And that's what I showed in those cores, which appears to be about a half to 1 ppm of mercury. Then when mining occurs, this is the pink line, and so you're going along, the concentration is roughly the same, but then it really creates a big zone of dispersion, a contamination around the mine site, and then it's observed way out into the oak's arm in the core that I pointed out earlier. And so then finally, as you get further and further away from the mine site, it goes through the dispersion dominated zone, it tails back off to a new I wouldn't call it background, but it's to a new level. And then finally, the yellow is after a remedy has been installed, then this distance should become smaller because the dispersion dominated zone should theoretically drop off. Anyway, I'm going to go through a couple more slides like that. I hope that didn't knock you out too much there, but here's another look at it. The same sort of conceptual model. This is just in sediments. So again, the 0 point, this sulfur bank mercury mine, this is way the heck up the upper arm, and it shows that pre-mining, which is red, that it was roughly 15 ppm mercury, and then it tails off through the dispersion dominated zone and then back to background. This is kind of the regional background, I would call it, for this area. And then this is post-mining, where the dispersion zone has become tremendous, where it's affected out, roughly several miles, because you can observe it in the oak's arm core as well as the upper arm core as well. And so this is the new minima that I described earlier, and I said I wouldn't call it a new background, but it's just the new minima. And if you think about this, the area between these two curves represents the contamination that really is present there. And there really, if there was to be a true cleanup, which is probably not possible because of cost, you would have to remove all of the area between these two curves. That would be the goal. Okay, and I'm just showing the breaks between zones 2 and 3, and zone 3 is the natural background, zone 2 is the dispersion dominated zone in both of these. Okay. So here's another, a similar approach here. Expected spatial distribution of post-release contaminants of concern in solid and liquid phases. Now, I have this normalized, so this could be mercury, it could be any contaminant that is associated with the mine site. If you're assuming that they're transported at similar rates under similar processes, then you could use essentially the same curves that we're using here. Okay, so you have flow from up to the upper arm, lower arm, and you have tributaries coming in, and that's what's creating some of this dispersion. And this is the natural conditions, or this is during mining. I'm sorry. So this would be the sediments. So you would expect those to fall out first, just to gravity separation, and then there's also further out. There's going to be a contamination that's associated with the suspended load that's in the water column. These are going to be mostly colloids and fine particulates. And then finally, you have the stuff that's dissolved, or a colloid, and it's being transported predominantly, in my opinion, by the plankton. And that's how you can see the effects so far from the mine site up into the upper arm and lower arm, is that somehow that mercury is being transported, and it's not the heavier end of stuff. It's actually the finer stuff and that's the harder material to address. Okay, these are out of that compendium. This was a tracer test that was done by UC Davis. They let some sulfur hexafluoride out into the water column and supposedly track this, or this is a model of it. And it's carried on day 142 by the surface elements currents to the westernmost end of the oak's arm and then into the lower arm. So it's kind of interesting. This is all kind of a modeling endeavor. We don't know if it's true, or if it's geofantasy, but it suggests that it's pretty complex. It's not a typical riverine habitat where you would expect If it were, it would start at the location and flow downstream. And that's not the case. There's a bunch of complexities associated with the currents that I believe are also associated with the wind currents. This is the conceptual site model from that compendium, and it's pretty good. And it shows all the different cycling going on. This is the mine waste. This is right here by Elem again, and then it shows contamination. The groundwater entering but also sediments entering, and just the complexity of what is occurring out there. The only the downside that I see for this, I thought it was a pretty good conceptual site model, shows the interaction, is that I think it undershoots this cyanobacterial bloom. I think this is probably the big driver that's responsible for redistributing most of this stuff out into the water column, where it is it scrubs the water column essentially. The cyanobacteria. It's because it's a organic compound. Okay, here's some work that from the compendium also, and it shows the range and mean of total mercury wet mass in the abiotic and biotic matrices of the Clear Lake aquatic system. So we have the concentration of mercury in water. It's definitely higher in the sediments, depending on where you sample it. But it's these higher ends are probably right by the mine site. Then you have plankton, chironomids, oligochaetes, and etc. You have the rest of the flora and fauna here. The most important one to me is the plankton. It shows the plankton is higher than it is in the water column, and it's substantially higher. And what it tells me is that let me back up. Excuse me. Is that the total mass of plankton, cyanobacteria, is enormous in comparison to the other masses involved here, and it's enormous, and it is concentrating. It's concentrating it up chain to the plankton, where then it is being buried. And I'm going to show you some more slides of that again here in the future. This is another very interesting slide from the compendium, showing the temporal trends in the percentage of total mercury in the dissolved fraction of water from 1992 and this period of 94 to 98. So what I see in this is, from in these boxes, is that total mercury builds in surface water during the months when algal blooms are absent. So it's essentially, it shows that it's building, and then bang, summertime hits, drops off, back down. Then winter hits, builds, and then drops back off. That's telling me that that and the previous slide indicates that the plankton is probably very directly related in the transport, and the ultimate endpoint of the mercury itself in the sediment and then in the fish. Okay. So back to that. That was, a very important slide. These just shows the difference between bacteria and cyanobacteria. This cyanobacteria on this side. The thing that's kind of interesting that I discovered is that cyanobacteria will only concentrate on the exos, or not methyl mercury, but just mercury, will concentrate on the exterior of the bacteria, and part of that is because of this plasma membrane. Well, it won't pass the plasma membrane for bacteria. The methyl mercury, on the other hand, will pass this barrier, and you see how much closer the barrier is to the surface than this barrier for the bacteria. So you get a double whammy. You get methyl mercury is concentrated inside the cell, and then total mercury is concentrated on the outside of the cell. And so this stuff is very effective at scrubbing the water column and being deposited at depth in the lake as sediment, ultimately. Okay, these are some sediment. This is from the core data again. This is upper arm, and this is Oak's arm, and it shows that in the upper arm, post 1927, this is 1927, is that fining is occurring. We're getting very fine sediments in the upper arm here, and not the case here at Oaks, because this is when mining happens. So you're getting a coarsening actually, and then it reverts back to fining more again later on after the mining shuts down. So what's the importance of this? It's fairly important because it also lends credibility to what is actually causing the mercury to be transported. This is a slide from the compendium also. This is what I would call the money shot. This is upper portion of the core, deeper portion of the core. You see all of the different flora and fauna. In the older core is much different. And it shows that this is getting finer as you go from D, C, B, A. You're getting into the cyanobacteria dominated stuff between A and B. So it shows that it's definitely the flora and fauna of the sediment itself has definitely changed over time. And again, this is mostly organic material, and it's really great at sorbing and scrubbing total mercury and methyl mercury out of the water column. And so this is an article, but removal of heavy metals by bioabsorption using cyanobacteria isolated from freshwater pond. They even use, organics are used in water treatment process to help sorb metals and polish water before it's sent out to be drinking or drunk. Okay. Again, don't want to beat this into your head, but this is the typical, conceptual model where near the mine, coarse sediments are deposited, and there's no way that these would be found way up in the upper arm. It's just the gravity would not enable that. Everything's suspended out, and then finally the transport is happening predominantly via colloidal and also as dissolved in the water column, where it is finally being scrubbed out by the cyanobacteria. So the reduction of plankton cyanobacteria will reduce the sequestration of mercury by the lake. So that these are some steps to reduce the mercury in the lake that I threw together. You want to break the mine, which is Operable Unit 1, to the lake transport pathway. And that's the tribe's alternative who does this. Otherwise, you're always going to have a source to the lake, and it's going to always be feeding the system. You want to remove near mine sediment, the mercury, especially ones that contain mercury hotspots, via selective dredging. That's what we were looking at along the beaches there earlier at Elem. And then finally, you want to reduce the production of plankton cyanobacteria in order to reduce the sequestration. This will allow a good portion of the majority to pass through the system downstream to the ocean, like it always had done in the past. Okay. Well, that completes this discussion. I'm sure I'll have another one. But stay tuned, and we will be updating the website with some of our written comments to EPA as soon as possible, and we will keep everybody updated on the status of the alternatives and where they land. So again, thank you very much for your time. Take care.